Once your town has fire, you have a lot less worries about your house.
How you doing?
Good.
Busy. I
You want to use the microphone?
last Monday I needed to get an internal.
Okay, good afternoon, everyone. I'm pleased to be giving today's department colloquium. My talk will be, as advertised, it's a little false because I'm going to talk about a particular flavor of potential vorticity. We're looking at the adjoint sensitivity to quasi-geostrophic potential vorticity. And this is based on work from an NSF grant. By way of I'm going to do a self-introduction. I begin first by saying something that's probably should be uniquely obvious or patently obvious to everyone in this room. We aren't who we are without the people in our lives that have helped us, loved us, supported us in the things that we do. And so I certainly acknowledge my parents and friends and colleagues. Just a little bit of history about me, since there's some folks that I don't know in this room that I haven't actually spoken with. This is me. At an early age, always interested in getting my hands dirty in something or keeping my office messy, as you see today. But I was always curious about the natural world. Part of this was fostered by the space program, NASA sending astronauts to the moon. My grandfather here, and my siblings, two of my older siblings, showing us something. This was from Crisfield, Virginia, at some point, pointing something out. He always had an interest in both, the physical world, biological world, things of that sort, and that inspired my interest in science in addition to my parents' supportiveness on that. But it wasn't really, believe it or not, John, winter storms that back in the late 1970s and early 80s got me really interested in weather. So here's this is the President's Day storm of 1979 that some of you in 452 have been reading some papers on, and some of the aftermath on my street here in Baltimore. And that kind of really captured my interest in atmospheric science. But upon going to college as an undergraduate, my conception of what I wanted to do was really more in frankly, the broadcast realm. I hadn't been captured. I liked the science aspect of it, but I thought, do that. So I did some on-air on the student radio station, WMBR Radio 88.1 FM. In Cambridge, we would, they'd have a news program, and I did the weather for that along with some other students. But over time, the science of atmospheric science really captured my interest. And as I said, from an early age, wanted to be an astronaut or an astronomer or whatever. That was the first focus. Then it was actually in sort of biological sciences and the physical sciences because of these snowstorms. But that was my first taste of weather, was perhaps more in the broadcast thing. But as a undergraduate and then a graduate student, my interest quickly moved toward the sort of fundamentals of understanding these weather systems. And so I was fortunate enough to land a position here at this university, which has been highly supportive of lots of things that I've had an interest in doing. I've had a couple leaves of absence from the university, National Science Foundation for a 4-year period, and preceding that, a year during a sabbatical leave working in the U.S. Senate on policy issues related to energy and the environment. So I've had a wonderful opportunity in a number of frames, from the basic sciences, to policy for science and science for policy, having those opportunities. But for today, my talk, and also the ongoing work I'm doing, is with several students, graduate and undergraduate students, and colleagues here. Zoe Britt-Lipton's doing work on adjoint sensitivity analysis of tropical cyclone dynamics. Karamar is, Elizabeth Maldonado has been working on singular vectors in the WRF model. That's an adjoint-based tool to look at generating an ensemble. Chen has been working on some of the work that I'm talking about today. She's contributed to, as well as it's a future direction for her PhD research. Isaac Schlushy's been working with me on getting a real-time WRF up and running and doing some really interesting work with that, in addition to perhaps putting some real-time adjoint sensitivities on the table. And I've certainly been blessed to work with great colleagues, Greg Hoover, John Martin, Greg Tripoli, on the work that's currently funded both for mid-latitude and tropical weather systems. So I'm going to give you a piece of that today and looking at the sensitivity of cyclones to various aspects of the quasi-geostrophic potential vorticity. This is part of an NSF-funded project to look at the relationship between the development and evolution of upper tropospheric precursors to surface cyclones. And so what I'm going to do is do a brief review of PV dynamics as well as adjoint sensitivities, including this newly developed tool or technique to calculate the sensitivity to PV, and I'll have applications of that to the 6-7 March 2020 Western Atlantic bomb. So here's actually the cyclone of interest, just to give you a sense of the cyclone we'll be looking at 12Z on the 6th of March last year, about 1,001 hectopascal load, right off the southeast coast of the United States, just south of the Cape Hatteras. And then with 12 short hours, it goes from 1,001 down to 973, an explosively deepening cyclone just off the mid-Atlantic coast. And then it deepens a little bit further over the next 12 hours down to 964 hectopascals. So a non-tropical, impressive storm. Can you believe it? Didn't have to have any tropical connection to it, but nice strong mid-latitude cyclone. And we're going to uncover the dynamics of this using some various tools, looking at the potential vorticity, but also looking ultimately at the sensitivity of potential vorticity and how that might be a really interesting tool to understand dynamically what these sensitivity patterns reveal to us. So in order to do this, I did a 30-kilometer wharf simulation. This shows the sea level pressure isobars every 4 hectopascal. Everything below 1,000 millibars is in red. So you can see this rapidly deepening storm. Broadly captures the track and the intensity change, not quite fully getting the intensity, but a pretty impressive development anyway. It's still a rapidly deepening cyclone off the East Coast. In terms of the hour-by-hour, sort of play-by-play deepening of the storm, this is over just for 24 hours of the simulation of this particular event. This is the 30 millibars in 14 hours, not too bad. But in reality, I put some stars on here. This shows what the actual deepening was over these various time periods. So the model didn't fully capture the deepening rate, but it did have a pretty good sense of, again, a rapidly deepening storm. It bottomed out around, as we saw, 964 at 24 hours into the forecast. But so we have a decent forecast trajectory to look at some of the dynamics of it. So the first thing I wanted to do is just sort of reintroduce this notion of potential vorticity as a key dynamical variable to investigate both mid-latitude and tropical weather systems, and more appropriately to look at what we call our term quasi-balanced atmospheric circulation. We'll kind of define that in a moment. And first of all, just acknowledging that there are various flavors of potential vorticity we can consider, from the simple absolute vorticity in a two-dimensional non-divergent flow, to the shallow water PV, which is sort of quasi-two-dimensional, but you have the ability to stretch the column, right? The column depth can change. The quasi-geostrophic potential vorticity, which will be the focus of this talk, and airtel potential vorticity, which is fully conserved in an adiabatic inviscid flow from the full primitive equations. You take those, or the full dynamical equations governing fluid flow, you can generate that this is a conserved dynamical variable of flow. So why is PV important in this? One is its conservation. It's useful as a dynamical tracer, so you can figure out where particular elements originated. And also its non-conservation is very revealing in telling us something about what sorts of processes may have occurred that led to PV not being conserved. And these dynamical processes or thermodynamical processes or frictions could be the culprit in the non-conservation. So just because it isn't conserved doesn't mean it's useless. It just means that there's something interesting that's going on that might be worthy of further understanding. Another point which is central to some of the things that I work on is this notion of the invertibility of potential vorticity. And what this means is, given a distribution of potential vorticity within some domain and some balance constraints, and by these balance constraints I'm referring to two of them. One, the relationship between the wind and mass field, or the height field. That's often derived from some approximations to the divergence equation. Either divergence is small, its tendency is small, or you can keep going into higher orders. That constitutes one of the balance equations. And then a relationship between sort of mass and temperature. Hydrostatic balance would be one state that we might use. You can recover from that, given the distribution of PV, the balanced within the constraints that are there, whether it's thermal imbalance type or a high order balance, the balanced winds and temperature distributions associated with a given PV distribution. So it's a very nice way of synthesizing all the aspects of the atmospheric dynamics into this single variable, which is nearly conserved, and allows us to look at how the atmosphere evolves in time by looking at how those distributions of potential vorticity evolve. And then perhaps a less well-known but still important aspect of potential vorticity, which we're going to build upon, these three notions will get built into the story that I'm telling, is the superposition of potential vorticity, which is basically a statement that you can bring two like-signed potential vorticity anomalies closer together, and in doing so, you increase the overall energy of the system. And I'll show a demonstration of that just in a schematic sense in just a moment.
Excuse my energy, what do you mean, kinetic energy?
It could be kinetic energy, or it could be a pseudo-energy, which is sort of a measure of the square of the kinetic energy plus something that looks like potential energy. Sure. I'll show that expression in a moment. So, as I said, these are the, PD is this key dynamical variable. These are the characteristics, but conservation, invertibility, and superposition make it a really valuable variable to diagnose the dynamics of weather and ocean systems that nearly obey these balance constraints. So we're not going to say it's strictly non-divergent flow or strictly geostrophic flow. We're going to allow that flow to be nearly non-divergent and have a small component of the flow which is divergent, which allows for a description of a secondary circulation, which is going to be responsible for the weather that we see with these systems. And we can look at PV in terms of looking at cyclones, both tropical and extratropical, mesoscale convective complexes, blocking patterns, as well as jets, can all be described and their evolution diagnosed from this potential vorticity perspective. So here is an example from that simulation for this storm. On isentropic surfaces, the 295K isentropic surface, 315K isentropic surface, the evolution of PV on these surfaces. And what you can't see explainable by simple horizontal advection on these maps indicates that there is some non-conserved process that's going on. So we see the increase in potential vorticity out here south of Cape Cod in this simulation. That's definitely going to be associated with some sort of diabatic redistribution of potential vorticity, likely this isentropic surface being beneath the region of intense heating associated with latent heat release in the cloud head of the cyclone as it evolves. On the right side of this, at a slightly higher level, you can see this PD structure marching eastward into the Atlantic, and there's some erosion on the leading edge of it, kind of sharpens up this little, they call it a trough, a minimum in potential vorticity that's just over in this Cape Cod area, which perhaps is the eroded part of the PV in the mid-troposphere. You see the redistribution of higher values beneath this. Again, you want to do a complete PD budget to fully see this and appreciate it, but that's one of the aspects of this. And we might, if we were to look at the precipitation associated with this event, you would see significant heavy precipitation in this developing weather system off the East Coast. So we're going to look at not aerosol potential vorticity, but the quasi-geostrophic flavor of this potential vorticity. As you recall from QG theory, you break your geopotential field into two parts. A part that's spatially, it's invariant with respect to, in the horizontal, just a function of pressure. That's sort of the large-scale basic state distribution of geopotential, plus a perturbation geopotential that's fully a function of x, y, p, and t. You can define the potential vorticity fully as Bretherton did, right? Francis Bretherton did with this is the sort of a classic form of the potential vorticity. But you have two additional terms which represent, at least in a conceptual sense, when you're inverting this potential vorticity, a term which is associated with temperature perturbations at the lower boundary, which we'll take in this discussion to be about 1,000 hectopascal. And if I'm inverting this potential vorticity, I have a lid somewhere, I have a potential temperature perturbation at the upper boundary as well that can be viewed as a contribution to the PV, but it's like a delta function of PV just in the upper boundary, the upper lid of my inversion domain, as well as the potential temperature perturbation at the lower boundary also acts like a PV delta function just at the lower boundary. So what this really means in the real world is that we can see a dynamical equivalence between potential temperature perturbations at the upper and lower boundaries of our domain, and that warm anomalies at the surface are dynamically equivalent to cyclonic PV anomalies just inside the surface. Cold anomalies at the tropopause are, again, just like cyclonic PV anomalies just below the tropopause, or the lid, the upper region of our domain. Our definition of potential vorticity, the perturbations or anomalous potential vorticity will be QP minus F, and we can further break it down based on time means. But we get just an equation that looks like this with this operator script P that operates on the geopotential perturbation, P prime, so that in principle, given the PD and boundary conditions, given latitudinal, the distributions of where the PD is located, we can identify this PD perturbation. We can invert this equation to solve for the geopotential. Right here, the geopotential perturbation. Given the geopotential perturbation, we can calculate the winds and the temperatures associated with this potential vorticity anomaly. So everything we need to know about the dynamics of the system, at least within a quasi-geostrophic framework, is describable or described by the potential vorticity. If we want to get things like vertical motions, an omega equation or something of that sort, we need to look at the time tendencies of the PD to get that. Okay, so I can invert, when I use the term invert, I'm not solving for the geopotential, and from those geopotential perturbations, getting the winds and temperatures associated with it. And of course, if there are questions, please ask. Please ask.
What is S?
F is the Coriolis parameter.
No,
S
S.
is the stratification. Measure the static stability. So, seeing this picture before, the sort of cyclogenesis from a PV perspective, we can have an upper level potential vorticity maxima that has a dip in the tropopause, so this would be our dynamical tropopause having some sort of depression in it that creates locally anomalous, associated with locally anomalously high potential vorticity. That cyclonic circulation can extend down to the surface. And if it interacts with a low-level baroclinic zone, that circulation can begin ejecting warm air northward, cold air southward, and eventually create a warm thermal perturbation at the surface. That warm thermal perturbation at the surface, as we saw from Bretherton's generalized PV, is going to be dynamically equivalent to a cyclonic circulation in the lower troposphere. That could potentially interact with the PV maxima aloft, and you can get this potential interaction, synergistic interaction between the upper tropospheric PV anomaly and the surface thermal wave to get a baroclinic wave, a cyclone beginning to develop. And this description is complete in one sense, to describe how the cyclone formed from a PV perspective and just look at the changing magnitudes of the anomalous PV. But notice this was all describable without having to necessarily point toward vertical motions and column stretching and vorticity. But it's all consistent with that, which is a nice thing.
Looks a lot like John's book.
I'm sorry?
This looks a lot like John's book.
From John's book, and this is a picture from the, also developed from Hoskins and McIntyre Robertson as well. So the credit should be on that. So for this simulation, what I'm going to do is just show a little bit about this inversion. This is looking at air-tail potential vorticity, and just looking at the structure of the dynamical tropopause as viewed through this cross-section that's viewed here. All right? So we have this PD trough that's located over just off the east coast. So I'm going to do a vertical cross-section. The leftmost or westernmost element of the cross-section is here. The rightmost at 30 north, 60 west is right there. And when we do that, look at the PV from about 125 hectopascal down to about 925. I'm going to define the upper PV structure being above this tropopause depression. Mid PV is this chunk right here, and the lower PV is what's shown right here. And then I'm going to take time averages of this, all these different slabs, to define the departures from that will be the anomalies that I'll ultimately invert. So here is the PV in the mid-troposphere having been inverted. This is not the PV, this is the heights associated with the potential vorticity in the mid-troposphere. So we have a minimum in heights here. Again, we can imagine from a time average sense that this upper trough is propagating eastward. At some point it's located at this location, and the heights are going to be lower here than they otherwise would have been if the trough weren't there. We have anomalously high values of potential vorticity upstream, of heights upstream and heights downstream of this. But what's going to be interesting then is not just looking at the fact that we have anomalously high PV here, which means a lower geopotential, a negative geopotential perturbation. What does that geopotential perturbation look like at other levels? So if you take that geopotential perturbation from the mid-troposphere and look and do the inversion of the PV and look at it in the lower troposphere, you get this minus 80 decameter minimum near 1,000 hectopascal. At this time, I've also included the sea level pressure isobars for this every 8 hectopascal, so it doesn't get too cluttered. And you can see the minimum the location of the geopotential height minima at the surface relative to the sea level pressure minimum is slightly displaced, looks a little bit upstream, which is going to be good for development. You can see the flanking ridges or anomalously high values of geopotential at the surface, anomalous geopotential at the surface associated with mid-tropospheric PV. Again, one of the locations you might expect.
What time is it?
This time right here is at 9 hours into the simulation. Thanks. At the same time, if I take then that mid-tropospheric PV, take the geopotential heights I just showed you, height anomalies that I just showed you, I can calculate winds from that, right? I can take that, take K over F across the gradient of geopotential. That gives me the winds. Now on this plot, I have, again, the sea level pressure isobars every 8 hectopascal. I also have in purple the potential temperature analysis at this time. And you can see the winds associated with that mid-tropospheric PV anomaly, what the impact is at the surface. And you can see it's helping to intensify this warm thermal ridge to some extent with the warm reduction in the warm sector of the storm, pretty robust associated with that circulation. Additionally, you can see that there is some evidence for stretching deformation occurring off the southeast coast of the United States, which would, in principle, help to intensify this front. You can do a, measure, calculate the frontogenesis there and see that's a pretty active front there just off the southeast coast of the United States. That would be intensified. Whereas for the warm front, at least by my eye looking at this, there's not much in the way of frontogenesis occurring due to that strong cyclonic circulation along the warm front part of the cyclone. So that's what's the mid-level PD doing to the surface, and one aspect of it is it's helping to intensify, to some extent, the warm surface temperature anomaly in this region, and helping amplify cold anomaly to the southwest of the cyclone center. That's all kind of old school, well-known, kind of expected. And a lot of this is kind of a review of the notion of PD inversion, but we're going to use it, we're going to flip it in a second. I can also ask the question, if I take the surface thermal anomalies and I were to invert them to get the geopotential heights, what do I see here? So you might see these two, this slide, the next one maybe, I'll go back and forth between them. But we see where we have the surface warm anomaly to the southeast of the cyclone center. That's this area right here. This is the temperature perturbations we're seeing here at the surface. A warm anomaly at the surface, cold anomaly at the surface. Remember, warm anomaly should be dynamically equivalent to the cyclonic PV anomaly just inside the surface. There's your cyclonic turning of the wind right there, as well as the minimum of geopotential associated with it. And this is in meters. So a significant impact at the surface for this particular event. And then other parts of this map, where this warm anomaly into the central Canada and then down into the northern plains of the United States, where it's slightly warm, we also see a cyclonic signature that when we invert that to get the winds, or to get the winds. All right. The nice thing about this, which I think is kind of interesting, was looking at this, is that along this warm front, you can see, clear evidence of sort of a confluence of frontogenesis that's occurring along the warm front with these components of the wind that are in the warm sector directed toward the increase the baroclinic zone, but north of the baroclinic zone, the flow is more right along the isotherm. So you're getting just a component of the flow associated with a warm anomaly at the surface helping to amplify this frontal-like structure. And perhaps the same thing with those shearing and confluent frontogenesis along the developing cold front at this time. But again, some of the lessons we can learn from this PD perspective on the cyclone. So that's the invertibility principle, right?
No,
Okay. And then finally, the superposition principle. And this is going to play a role in the development again that's coming forward. So this basically states that if you take two cyclonic or two like sign potential vorticity, or in this case vorticity anomalies, if you look at the barotropic case, and bring them closer together, you will that leads to an increase in the energy of the energetics of the system we're looking at. We can define that kinetic energy, at least the part that's associated with the rotational part of the flow, as -1/2 the inner product of the, almost correlation between string function perturbations and the vorticity perturbations integrated over the area. So if we consider two like sign PV anomalies, both of them positive, in isolation, when we invert that PV anomaly, that positive or cyclonic PV anomaly, we invert it, with boundary conditions that are at a great distance away, we're going to see that each of those, the anomalous stream function associated with both of them, both pairs will be negative, right? Positive PV anomaly is going to be associated with a minimum in geopotential or stream function in this case. So we know that these are going to be opposite sign. So if I do the calculation, maybe it's best to show the picture. So here are my two positive PV anomalies, cyclonic circulation around them. Notionally, we have these dashed contours indicating a negative or minimum in geopotential at the center of these. And what we're going to do is we're going to bring these closer together. So before we bring them closer together, the kinetic energy is going to be minus the 1/2 the vorticity associated with this anomaly times the string function associated with this anomaly, plus minus 1/2 the vorticity associated with this anomaly times the string function associated with this anomaly. Right? That's what we have here. When we bring them closer together, we're not really amplifying the PV, but the overlap between these fields is going to go up. So the string function anomalies are going to be additive. The vorticity anomalies that the total string function pattern is going to influence or feel is going to be, it's going to be this expression, right? String function is going to be additive. This, minus 1/2 this total string function distribution times this vorticity anomaly, plus minus 1/2 this total string function perturbation times this anomaly gives us the kinetic energy after we brought these like sign PV anomalies closer together. We take the energy before minus, or the after minus before, and you can work through the math, you'll see that we get an increase in the kinetic energy through this process. Yes?
What about the entropy? Doesn't that go with the square?
The entropy goes by the square of the vorticity, but I haven't thought about how that's going to how that calculates in this. This is just a calculation of the energy itself, the kinetic energy associated with each of these vorticity anomalies. So the entropy would, which goes like the square, would also go up. Here is and one way to think about it is, the winds, when these two anomalies come together, the winds are going to add up linearly, right? But the kinetic energy goes up as the square of this wind, and so this sort of triangle inequality, you can see that the sum of the squares of the energy of the kinetic energy without the 1/2 there, individually it's going to be less than, since the winds are in the same direction, it's going to be less than the square of the sum of those wind components.
So presumably, if the kinetic energy goes up, it must be converting from something.
Right, so whatever process that's associated with a larger scale flow that's bringing these structures closer together, it's going to have to extract energy from whatever that process is. And that's not described in this, it's just if you bring them closer together, you will get higher energy. But you're absolutely correct, it has to come from somewhere. That would be one of the large scale flow that's starting to make these, come closer together. Okay, and I note here, this result is generalizable to 3D QGPV distributions as well, and we'll see that expression in just a moment. We're about to do a switch. We talked about invertibility, conservation, invertibility, superposition, those three concepts. And now we're going to combine these ideas into coming up with a technique that allows us to synthesize the results from an adjoint model, which I'll now describe. Okay, so, talk about adjoint models, adjoint sensitivities. What is an adjoint model? Well, fundamentally, at the coding level, if you have an NWP model, numerical weather prediction model, the adjoint model is really a line-by-line matrix transpose of each of the lines of code in that model that associate with the linearized NWP model. And that might seem like a very abstract concept. We're not going to have to develop one right here, but the key thing that I'd like to leave you with on this is that the adjoint model is a tool that's used to calculate the sensitivity of some function of model output, we call that the response function, to changes in the model input. So the adjoint model doesn't calculate a perturbation, doesn't calculate the basic state. It calculates how changes, small perturbations to the initial state of a model will lead to changes in some function of the model output. displayed here. So you can have a nonlinear forecast model like the Whorf model, the GFS. We have an initial state vector that describes all the information that you need to know state of the model at the initial time. Goes into the nonlinear model, produces a forecast. And then for our purposes, from that forecast, we might be interested in the intensity of that East Coast cyclone that I mentioned earlier. Well, we can calculate how the intensity R, that response function of the East Coast cyclone, changes to changes in the model initial state. That comes from the output of this adjoint model, which has as its input the sensitivity or the gradient of our response function R with respect to the model state at the final forecast. Once we get this particular change in response function, this gradient, this sensitivity gradient, we can take the dot product or inner product of the gradient with any arbitrary initial perturbation and figure out how does the cyclone intensity, in this case, R, change. So X prime right here, X prime naught, would be an initial condition perturbation. It could be the temperature at a grid point. The temperature is all over South Dakota. It could be a wind component in South Dakota or a wind component in Florida. At the initial time at a given grid point, I can multiply that by the sensitivity of that grid point that I've calculated from the adjoint model. And that would tell me, at least within the context of linear dynamics, how much would that response function change. So I want to take you through, we're not going to go through all these equations, but a couple peculiar aspects of the adjoint model that we're trying to resolve. If you look at the shallow water system, which may be familiar to many of you, look at these first three equations here. The momentum equation has been linearized about a basic state at rest, Meridian momentum equation, and the shallow water height tendency, or depth tendency equation. You could actually, you could linearize, now this is already linear, but you could take the adjoint of this system that gives you this. I won't go into lots of details, but these minus signs here in front of the time derivatives indicate a backward integration in time. These hats over the variables indicate sensitivities to the U, V, and shallow water depth, perturbation depths. These are all sensitivities to these variables. And so what I want to do is to show you not a thought experiment, but a numerical experiment that you could do with this model and some of the interesting output that comes from it. Then we're going to come back and look at the Whorf, a case for the full physics Whorf. So I'm going to take the shallow water system and imagine a situation at the final time. I don't know what the initial conditions were when I created this, but I'm interested in what perturbations can I make at the initial time to strengthen the westerly component of the flow in this particular region. So the end output of my model is some measure of the westerly component of the flow. I'm using a functional form right here that describes the U and V components of the flow. There is no height perturbation at the initial time. There is no V sensitivity to V at the initial time. It's just a zonal flow that looks like this kind of Gaussian, it decays in that direction. So the vectors here show sensitivity to wind. The fill patterns you'll see in a moment show sensitivity to height. And then I have sort of what I've predicted to be the long-term sensitivity to height in these dashed and solid contours right here. I'm just going to step through a couple things. You're going to see an animation later on at the conclusion of this talk that wraps everything together. But if I go back 1 hour in this shallow water system to mid-latitude domain, thousands of kilometers that are shown here, what happens is I immediately see sensitivities to height beginning to pop up here. What does this mean? If I wanted to increase in 1 hour's time the zonal component of the flow right here in the middle of this diagram, I could do two things. I could make the flow, the perturbation depth in this higher here and lower here, which would cause the fluid to slosh toward the northeast, or east-northeast. Or I could increase the component of the winds that are from the west-southwest in this direction, the direction of these arrows, and within an hour's time, the Coriolis force is going to torque them to the right. So I have two options. I can perturb the winds, I can perturb the height field, and the adjoint model tells me precisely where I want to perturb. These vectors that are shown here, again, sensitivities to the wind, but I can immediately convert them to perturbations I want to put into the model. And it tells me precisely where I want to increase the westerly and southerly component of the flow right here if I want to increase the net westerly flow in the middle of this domain. Again, these contours here, don't worry about them just yet. If I wanted to perturb the height field of these regions, pile up the fluid here, decrease the fluid here. That's going to create a sloshing effect as the gravity adjusts everything, and then it gets rotated by the Coriolis. I can go back further in time, and what's seen in this integration is I get these gravity wave-like structures that begin propagating outward. This looks very much like geostrophic adjustment. In fact, it is, but it's in the adjoint system. And it creates these gravity waves. So my contention is that when we look at adjoint sensitivity fields in the real atmosphere, one of the things that kind of clouds our interpretation of them are these gravity wave-like features that rapidly propagate outward from our initial adjoint field as we march our adjoint model backward in time. In fact, if I wait long enough, 18 hours, those disturbances will propagate out of the domain, and I'm left with a field that looks something like this. This would be like the sensitivity 18 hours earlier. If I want to increase the westerly component of the flow, one thing I could do is just simply put lower heights here, higher heights here, and that will give me a westerly flow that's perfectly in sync, or I could increase the westerlies already in this field, but I probably want to balance it with a low to the north or high to the south. That may be an obvious answer, but what happens to those divergent parts of the flow?
Does this also tell you implicitly then the time scale of the
evolution,
adjustment?
Yeah. And that adjustment time scale you could calculate is going to be very similar to the one in the Ford model, in the normal shell.
So you know that, almost know that going in?
Yeah.
Okay.
You know it going in. But again, it's these features here that look like gravity wave type structures that are kind of distracting in real data, and in this very simple model we see it. So there's a solution to that. We'll get to the solution. So for the Whorf model, our state vector has UV-W theta P prime moisture. We're not going to look at moisture, the impact of moisture in our sensitivities for this run. But the adjoint model for the Whorf calculates sensitivities to U, V, W, theta, and P prime. And you can plot those sensitivity vectors as I was describing it. But we just spent the first half of this talk talking about potential vorticity, or talking about vorticity dynamics. You know, if you look at if I go back to the plots I was showing you earlier, like this, I just showed you a bunch of vectors like this that shows me the sensitivity to the U or V components of the wind. Well, I can easily identify, if I increase the southeasterly flow here, 4 hours later, I'm going to increase the westerly flow in this region. And you might be able to understand how that happens, or from the height fields as well. But no one really looks at, or at least I don't look at, as a synoptician, I don't look at weather maps and look at a given region and say, this is the zonal component of the flow, and this is what it's going to do, or this is the direction of the flow now, and it's going to have some impact 4 hours later, it will look like this. You know, to make this interpretation a little bit clearer, if I look at things that are more, I can sink my teeth into that are synoptically relevant, like vorticity or potential vorticity, it might make the interpretation a lot simpler. So one of the things we did a while back was calculate sensitivities to vorticity and divergence from what the model outputs sensitivities to U and V, and that works out quite well. I'll get to the more fun stuff in just a second. And so what I'd like to do is figure out a way to take sensitivities to U, V, and theta from the model and calculate a sensitivity to potential vorticity. And the way that we do this is by making use of an interesting, all the things I talked about before, conservation, invertibility, and superposition, allow us to come up with a way to calculate what we call these optimal initial conditions in a model. So if I take sensitivity gradients, I've calculated them, and I ask the question, how do I put the minimum energy in my model at the initial time to grade a particular change in my response function, say 24 hours later? This is what's called an optimal perturbation. I can measure the size of the energy of the perturbation by this inner product that I've written down here. And Greg was asking, you know, what's one form of that inner product? It could be something like this, an energy term, kinetic energy term, note the 1/2 here, and then a term that looks like the square of temperature perturbations along model surfaces. Not quite a potential temperature, not quite an available potential energy, but it's something like it. But it has all the hallmarks of an energy, and you can look at it as the inner product of an initial perturbation times some weighting matrix and that initial perturbation. If you ask the question, what perturbation do I have to put into the model at the initial time to produce a particular change in the response function, delta R, it turns out you can write this out as a Lagrange multiplier problem. You take the energy plus lambda, the Lagrange multiplier, times the constraint, turn some cranks, you'll get that the initial perturbation that you want is going to be given by this Lagrange multiplier, which we can actually calculate, the inverse of whatever the weighting matrix was, and for kinetic energy, that weighting matrix is just the identity matrix, times the sensitivity gradient. So I'm creating initial perturbations in my model that are proportional to the sensitivity gradients I get from my adjoint model, and these will allow me to affect a change in the response function by a certain amount, delta R, in this case 24 hours later. Look at the setup. Remember, x naught is my state vector, is the perturbation, or x naught prime is the perturbation state vector for perturbations to the initial conditions that I'm making. Every single variable has the same Lagrange multiplier lambda. The sensitivities that I get from the adjoint model are here. All that's important is this weighting matrix W. And so, a former student of mine, near the end of his PhD dissertation, was Alex Goldstein, was thinking, well, doesn't that just simply mean that the optimal initial condition perturbation for QGPV, the sensitivity to PV, I can simply just divide through by lambda W inverse times the PV anomaly or PV perturbation, I've gotten my sensitivity to PV. And we knew that didn't look quite right, but we sort of puzzled over it for a little bit. And then came to the conclusion what's going to be key is this weighting matrix W, because W is going to be different for PV. PV is not in my state vector, Q is my PV here. It's not in my state vector. So what is the weighting matrix that's appropriate for this? And this is where all the prior stuff that I've shown comes into play. Remember, kinetic energy is given by minus 1/2 stream function times vorticity integrated over an area. Well, we can write that in this form. There's the minus 1/2 stream function times vorticity integrated over an area. How do I relate the stream function to the vorticity through the inverse of my Laplacian? And so my weighting matrix is getting minus 1/2 the inverse Laplacian. You can go through, make some, I won't go through the math right now, but I'd be happy to take someone through it. You get the expression for the sensitivity to vorticity is given by minus the inverse Laplacian of this expression down here. And that's an easy thing to calculate using SOR. And that matches expressions that we derived years ago from a totally different procedure. We can do the same thing to get sensitivities to PV. So this is what I'm calling a pseudo-energy associated with the geostrophic wind, the kinetic energy associated with the geostrophic wind, plus 1 over S, which is that stratification term, times a T prime squared, dV. You can go through the integration by parts and show that this actually gives you the energy is given by this inner product of the PV times the geopotential. How do we get that geopotential? It's through PV inversion. There's our inverse operator P right here. And so our weighting matrix is going to be 1 over F naught, or minus 1 over F naught, this inversion operator. And just to jump to the punchline, here's our sensitivity to PV. That's based on this notion of creating an optimal perturbation, a recognition that the Lagrange multiplier in all these problems is a shared number for all the variables. And what's key is how you define the energy so that you can actually get the right expression. And so this is our sensitivity to PV. How do we interpret it? So it's minus 1 over F naught, this inverse Laplacian, or this inversion of this elliptic operator. We have the curl of the vorticity here, plus something that looks like a stretching term. If you actually look at it, and sort of you can convince yourself of this, that if you know the sensitivity to PV is positive in a region, that implies that the sensitivity to the other more basic variables, U and V, are going to have patterns that look like this: negative sensitivities to U in the north, positive sensitivities to the south. It all looks like a geostrophic balance. This is in the horizontal. If you do a vertical cross section, you should see the low positive sensitivities to PV. You'll see a negative beta sensitivity to temperature, and above it, a positive sensitivity to temperature, and flow in this cross section into and out of the void. So this is kind of neat. So let's see what it looks like in the real atmosphere. I go into my work model, run it forward in time to the final time, and I define this region off the East Coast that's enclosed by the 988 hectopascal contour. My response function is the average pressure within this contour, called minus mu prime bar. And I'm going to ask the question, and I put that minus sign there so that any positive sensitivities that we see imply that you can make a perturbation that's positive there. That will lead to a decrease in pressure in this box. So any positive sensitivities that I show you will be ones that if you put a positive perturbation to whatever that variable, that sensitivity variable is associated with, you will get a stronger cyclone off the East Coast. So before we go into some examples of this, here's our cyclone that's beginning to develop off the East Coast. This is 6 hours of the forecast. The geostrophic vorticity, not the PV, but the geostrophic vorticity, has a pattern that looks like this. Maximum geostrophic vorticity is upstream in a thermal wind sense of the surface cyclone beneath it, so it's a nice configuration, at least at this level. This is roughly 500 hectopascals for development. If we ask the question, how sensitive is the cyclone development to PV at this same time, at 500 hectopascals, this is what we see. A large positive sensitivity to quasi-geostrophic potential vorticity located over North Carolina. Another interesting feature that's over Quebec, and negative sensitivities out over the Gulf of Maine and South Maritime Canada, and then back to the southeastern United States to just north of Cuba. What this says is, if this is a 24-hour sensitivity calculation, if at 6 hours into model integration, I were to go in and put in higher values of potential vorticity, QGPV in this region, 18 hours later, that cyclone off the East Coast would be deeper by a certain amount. I could actually calculate it. If I were to actually put less PV in this region, perturb the model state at this time with lower values of potential vorticity, so a negative PV perturbation, that would lead to a weaker cyclone out over here. So if I perturb the PV here, I decreased it, made this ridge a little bit more amplified, that would actually lead to a more intense cyclone 18 hours later. This kind of harkens a little bit to like a self-development like thing, with increasing the ridge downstream. Now, some of this is kind of, patently obvious. So you know cyclones and how they work, what's new in this. But this gives us a level of precision about where we want to perturb this variable, this dynamically significant variable, at a given time along the forecast trajectory to get a desired change at the final time. Yes, great.
Do you ever look at this at different heights?
Yeah, we're going to do a cross-section of this in a second.
Yeah, because, what I've been working on is that these things are extremely sensitive to how low the PV is at the upper levels.
Right.
And so that negative sensitivity for negative PV perturbation would give a positive growth tendency.
Right.
Which is what I do, but I would think that the negative one there is stronger when you get to higher levels compared to the positive feedback.
That's possible. I haven't looked at that exclusively for this, but that's one interpretation.
But Michael, what you said, I don't dismiss that this is just something we already know, because I'm seeing some geometry in the distribution of these anomalies that's very distinct. In the entrance, in the confluent region, those anomalies' long axis is perpendicular to the geostrophic flow, by and large. And in the trough axis, it's more or less parallel to it. And then when you get into the mixed region northwest of the trough axis, where we know synoptically there's interesting shear and curvature processes going on there, you get a mix.
Yeah.
And so there's transverse signals there, and then there's shear-wise signals there.
Right, and this all fits into how does that upper trough, the structure of it evolve during the cyclogenesis, and that which is the focus of the work
Yeah,
we're doing.
it's perfect. It's a perfect tool for that. Really cool.
Brandon.
Can you change either vorticity or stability?
Those two could be done separately, but whatever that change is, as measured by the PV perturbation, the dot product of that perturbed PV, whether you did a stratification change or a wind change, the dot product of that with the sensitivity to PV here would tell us exactly how much that change would be, in a linear sense at least, at the final time for this cycle. So I've already shown you this slide. We're now looking at some cross-sections through this. And I thank Noah for creating these cross-sections. This is a cross-section along the thermal wind shear from southwest to northeast. These are sensitivities to PV, and then we're calculating from this sensitivities to temperature. And you kind of see these structures that are tilted up shear, thermal structures in the vicinity of that strong shear, that are tilted up shear, and that's consistent with, frankly, a superposition type idea. You take these PV anomalies that are tilted a little bit, and then since this thermal wind right here, this is the thickness rate, the thickness distribution, then it keeps wind increasing with height in this cross-section, you gotta take structures and tilt them. That's bringing like-sign PV structures closer together, which would lead to an intensification. But it says sensitivities down here would be positive, positive, negative here, and this is some stuff that's further to the northeast. It's rather difficult, a challenge maybe to describe somewhat. But what's going on in the middle of this picture is kind of what we would expect.
Yeah, and we might have picked these on purpose, but that angle of that cross-section is exactly tangent to the spot of the upper vorticity maxima where the development's strongest. Because I saw that. That's where the PVA by the thermal wind is strongest, right on the Hatteras coast.
In the nonlinear simulation.
Right, yeah, it's a perfect decision. So maybe you already knew that, probably did.
So are you thinking about this in terms of latent heating at all? Like where latent heating would be?
You
know,
could,
mentioned
so
that
if-
was important, right?
Right, so if you knew that the heating distribution in your model, your forecast trajectory was goofy, you could then understand if I increase the heating here or decrease it somewhere else, what the impact would be on temperature. So whatever processes that give rise to a temperature perturbation or a temperature tendency, you could look at the projection of those onto the sensitivities to see how would that cyclone intensity change.
So you could see you're getting the latent heating wrong, that has this impact on the
Right,
intensification.
this wouldn't tell me the late heating is wrong, I need some other independent piece of information, but then the difference between whether it's a temperature profile or temperature distribution and of the control versus the perturbed simulation with better latent heating, that could then tell me exactly what I'm expecting to see
Sure.
for the impact.
So you could compare, like, say, observations to what the model
Exactly.
is doing for latent heating and look at what impact that would have.
Right.
If the latent heating was better
Exactly. On the cyclone development. John?
Yeah, so just to clarify, the model runs did have latent heating in
Yes,
them?
yes.
Okay.
But we know one thing, as an example, we know that this forecast is under forecasted for development. So I could perhaps back out to the extent that I have a perfect model or a nearly perfect model. Where was the deficiency in the heating? If I think the dynamics are right, but the heating was a bit goofy, I could ask that.
Compare the heating and reanalysis to the heating in the
Right.
model.
Dan?
Given that this is let me rethink the question, I'll ask later.
Okay. Here's another cross-section taken in the upstream northwesterly flow ahead of the upper trough. Here, again, these are the isotachs in gray. Sensitivity to PV is in the solid and dashed black contours, and then the sensitivity to the normal component of the flow in this cross-section is given by the shaded region. So this is no longer temperature, but the sensitivity to the component of flow normal to the cross-section.
So what's positive is
So positive would
means
be...
coming out or into the
Yeah, coming out.
Okay,
Yeah.
okay, thanks.
And so that indicates here that even though, here's our jet maxima right here, and on this side of the jet, I don't think we look at this again, it's 7794, so this is actually one that's a little bit awkward or backwards. So this side right here is on this side of the part there, so it's kind of backwards in that sense. But what it's indicating is a change in the shear along the edge of the jet is going to lead to a more intense cycle, could lead to a more intense cyclone at a later stage. And in the interest of time, I can come back to this, but changes in shear right here could also be related to maybe changing the level or the depth of a tropopause
Yeah.
fold that's forming. Could be hidden in this discussion.
So the colors are the sensitivity?
Right, to wind, right, not temperature, but to the normal component of wind in the cross section. I'll come back to this. I want to just,
So what are the solid lines?
solid lines are sensitivity to PD.
There's a negative sensitivity to PV on the right.
Which is maybe on this side. This, the order of this cross section is looking, if we were standing here and looking jetward, southward.
Okay, so it's the ridge. Sorry.
Right, so this is consistent with helping to amplify the ridge here and make the flow a little bit more.
You're gonna do a cross-section on the other side or something?
No, not in today's stuff.
Okay.
Sensitivities to PV. Remember we saw this picture earlier from mid-tropospheric PV. This is not sensitivity, this is the inversion result we had before. Here is the sensitivity to PV at the same time. This is in the flow. And you can see it's roughly in the same location, a little bit downstream of that, of the trough axis that we had earlier. So this is saying the sensitivity to PV increasing in this region, or increase the PV in this region, which is where we had the negative geopotential height minimum, which would be associated with a positive PV anomaly. This is a mixed up plot. So that's showing the geopotential anomalies. This shows the PV. You want to put it just where you already have the strong tropopause undulation. This is the sensitivity to PV at 850 hectopascal. And it shows this ring to the north and west of the cyclone center at this point. If you were to increase the PV in this location, this is 18 hours
At 8:50.
Right, at 8:50. So the 6 hours is the beginning of the simulation at 8:50. If you increase the PV back here, that would lead to a stronger cyclone 18 hours, or 18 hours later. So what are some of the lessons learned from this? So in the summary, we've exploited a result that from defining optimal adjoint-informed perturbations, we've come up with a technique to calculate the sensitivity to QGPV. And I didn't show it, although I was showing results from it. We can also get sensitivities to the geostrophic winds and hydrostatically balanced temperatures. I was showing that in some of the cross sections. This tool, which we first applied to the WRF adjoint model output, allows for a robust QG interpretation of the dynamical evolution of nearly balanced weather systems simulated using the WRF model. This can be generalized to other model output, but this is set up for the WRF model as an adjoint. And the tool paves the way for interpretation and application of sensitivities to airtel PV, which is another goal that we have going forward. So I want to go back a second to a simpler system. This is the shallow water system we talked about before. This is from Morgan 2018 paper that looked at the evolution of sensitivities in the shallow water system. We found a couple of interesting things. You know from the shallow water equations, you can combine all three of these equations to this equation down here, which shows that the forcing, at least for the time-independent part of this flow, this gives you basically an invertibility relationship. The long-term behavior of the shallow water system at rest, if you perturb it, it's going to be governed by whatever the PV distribution is. So the PV kind of locks things in dynamically in the shallow water system. You already know that, there's nothing new there. If you look at the adjoint of the shallow water system, kind of go line by line here, we find instead of the conserved variable being, well, in addition to the conserved variable being associated with a PV, like in the linearized shallow water system, we discovered the conserved variable for the adjoint of the shallow water system is a variable of quantity we call the balanced height field. This is conserved following the, if you perturb the shallow water system, this balanced height field governs the dynamics of the final response. So those pictures I was showing, and I'll show you in a second, of the evolution of sensitivities in that shallow water example, it's all governed by the sensitivities to this balanced height field, which is actually closely related to the sensitivity to PV. So PV still is central, but there's another variable that's a little bit simpler to understand. So I'm going to go to an animation of what we were looking at before. You see these gravity waves propagating out. These contours here that I didn't explain earlier were sort of what we predicted the final time sensitivity to height field should be based on the PV. And this was sort of a nice numerical example, but it worked out exactly as we expected. Better have, else probably wouldn't have published the work. But the thing is, the sensitivity to PV and the sensitivity to balanced height kind of govern the dynamics of this system. All these messy sensitivities, these gravity wave-like things, when you see them in the WRF model, they hit the boundaries, they can bounce back in, contaminating, ruining our interpretation of sensitivities to whatever variable we're looking at, wind, temperature. But if we can actually put in balanced perturbation at the final time, balance in a sensitivity sense, that would allow us to better interpret these fields. So to conclude, this also provides insight into how the mass and wind variables are related as we have this backward integration. based on prior work and what we're beginning to see here, this result also suggests something that the data that sticks in 4D VAR, four-dimensional variational data simulation, is going to be the balanced part of the observational increment. This is more a suggestion that we have not verified this. But what's going to happen when you do 4D VAR, which uses an adjoint model to integrate information backward to the initial time? It takes this difference between the forecast trajectory and the observation, and then integrates this piece of information backward. Well, that's going to be a non-balanced feature. It's going to radiate lots of gravity waves out. But what's going to stick is the part that's associated with what contribution to the PV are you putting in from this particular observation. That's speculation. We have to look at this a little bit more. But it may also indicate regions and situations in which certain data does not stick, if you will, in the backward integration. Might be places where you have significant non-conservative effects prior to the time the data is assimilated, and how well your model treats those conservations of PV and things of that sort. Initial perturbations that we get from this, if we want to do optimal initial perturbations, we can balance them out, so we have a nice smooth forward integration if we use this technique that we have for sensitivity to PV. And the backward integrations, again, can also be initialized much like NWP models were done a while back, so that you only get the salient pieces of information that are stuck to the PV if you want to use this backward integration. So next in this line of work, No Chen is going to be beginning to develop the infrastructure to do this for airtel PV, which I think would be a really nice tool that gives insight into how weather systems work in the framework of the WRF model. And from a PV perspective, that's better than just geostrophic balance. We could be using sort of nonlinear balance PV, sensitivities to PV to look at that. In any case, I've run out of time. Thank you for your attention. I welcome any questions. Questions, please.
Have you tried to put the balanced adjoint fields into your shallow water system?
Yes, I believe that we've done that, and what we see is we don't see much in the way of waves being triggered in the backward integration. So it suggests this notion of trying to get a balanced initial backward adjoint integration is going to be possible. John?
Can you go back to that 850 millibar case example you had right near the end?
Yeah.
And you said, I think I'm interpreting this right, and I think it's what you said, that if you can increase the 850 millibar QGPV back there,
Right.
18 hours later, you'll have a more intense cycle.
Right.
Can that also be interpreted in the following way? That if your simulation develops, because that's going to be the occluded quadrant of the cycle, where one expects eventually in a development you'll have some pretty sizable latent heat release and probably low-level PV generation. If it gets there faster than you expect, your cyclone deepens more. Is that another way to expect
I think that's one way. If you were to increase it, I mean, again, this is only saying something about the final time intensity.
Yeah, yeah.
But if you
And
were
you
to-
prescribed the final time.
Right.
Yeah.
So it's going to be difficult to say it's going to get you there faster necessarily.
But if you get here faster,
right.
then
You may-
you're going to get that intense of a cycle.
Right.
Okay.
That's great.
I got way too many questions to deal with right here now, but this is extremely interesting, and I think it's opening up a lot of doors. The one thing I see here is that with the QG system, there's a certain degree of things you're really missing with this in terms of the effect of convection and other things like that. But one way I look at this, which is a different way than you look at it, is what is the strength of the system depends to some extent on the vorticity coming in. But overall depends on how much energy can be converted from the energy source for the
Right.
system. And the efficiency of converting is actually opposed by the strength of the cyclone. Because as you get more and more balanced flow, that inhibits the rate at which you overturn, because it locks up the energy in a balanced system. What actually frees the energy is the ability to allow divergence to form.
Right.
And the divergence can form when the potential vorticity is low.
Right.
And so, to a certain extent, what you're looking at is the difference between the high and the low potential vorticity. When you raise the potential vorticity in one place, they're relatively different. So what you want to get is you want to get a way to form divergence at high levels. And you can do that by the insertion of low potential vorticity, which is a byproduct of convection or tropical plumes.
Right. No, you're absolutely correct. And this tool, we believe, both for tropical cyclones and extratropical cyclones, will allow us to diagnose specifically where you'd want to make these amendments to the PV, so you get that. But I think that related to what you said, a more interesting question, or an equally interesting question, would be, how do the perturbations that result when you make those changes dynamically allow for that release in energy?
To unlock the system.
To unlock the system, exactly.
That's right.
So that's another part of it, and Zoe's kind of looking at an aspect of that for tropical cyclones right now.
Good.
Yes.
Yeah, can you go back to the figure where it shows the, basically the spatial extent of the response area? Yeah, so I'm curious because I would think that if you perturb your initial state far enough away, or you perturb far enough away from the initial state, I would think that, maybe the centroid of the cyclone or the extent of the cyclone might change. So I'm wondering if that is a fixed spatial area.
Okay, this is a fixed spatial area, and I should have shown it. I intended to show it, but just in terms of time and things, when you put perturbations in there, you get, concentrated change in this region. But you're absolutely correct. If I had this response function region way too small, and I make a perturbation that knocks the cyclone out of the box, if you will, the region, that can lead to complications. So that response function box isn't fully, you can make it any size you want. You want it to make it so that it's interpretable if the cyclone changes position. This works out pretty well for this event. Yes, Dan?
Yeah, I guess this balance, the idea of inverting the balance sensitivity, I suppose, that you showed at the end there. Part of the final response is going to come from that, but part of it is going to come from the superposition of the waves that are propagating into that area. Is it just that the propagation of those waves is more distorted by the background flow, and so you can trust the initial projection onto those, or?
Yeah, so we actually had Noah and I were talking about this morning a little bit. It's more in the backward adjoint integration, where if you're really trying to interpret these fields in some synoptic sense, you get a problem when these adjoint, at least for the WRF, the way the adjoint model is formulated, these will radiate gravity wave-like structures, sensitivity patterns that look like gravity wave structures. They hit the boundary, they can come back in. Now, maybe it's all consistent within the model world, but they're probably not physical. I'd argue before they hit the walls, there is probably a physicality that's there, but how much of that is going to be either easily interpretable, or do you desire to interpret that part of it as opposed to the part that's more balanced? It might give you understanding that might give you a bigger bang for your buck, if you will. Other questions, please?
But for short periods of time. I mean, so those are gravity waves that are hitting the boundaries in hours.
In a few hours, right? It could be within 5 or 6 hours. You can sometimes see them get quickly out. They're really deep, external type structures that get out quickly.
Is there an equivalent of like a slower Rossby wave in there? I mean, I know it wouldn't be in the shallow water system.
No, it wouldn't be a shallow water system, but I think what you would see if we were to look at the sensitivity of QGPV along the backward integration and begin looking at animations of that, you would see a lot of that structure is probably going to be, I think it's probably going to be conserved following the adjoint flow going backward. And so it's going to be something that's evolved much slower than the gravity wave-like structure. But I haven't demonstrated that yet.
Yeah, I was wondering if the work model also shows you how well you know your geophysical variable estimate, and if you perturb, basically you have a certain perturbation, if you can kind of tell with the current certainty with this variable, we're kind of limited by this one variable to understand the development later.
Right, so you can get sensitivity to each of the variables independently in the adjoint, right? It's a partial derivative, so it's changing the U component of the flow. It doesn't care if you change the V component, right? It's DRDU is independent of DRDV since they're separate variables. But if you had a sense of, you have all these sensitivities and you have a sense of forecast error estimates, you could probably figure out what are the, or analysis error increments at the beginning, and you want to say, well, where am I getting the biggest bang for my buck if I want to put a perturbation in? It can kind of direct you to these are the most sensitive regions for these particular variables. perturbations to them are gonna make a big difference. Perturbations to these other variables are gonna be largely irrelevant.
Because it kind of ties into like, the observations and how good our observations are. So, similar to when it tells like, oh, we need better
Right,
observations.
right, so you can do sensitivities to forecast error
Yeah.
in this. Doesn't even have to go to the QGPV part. You can say, what's sensitivities? My response function is some trusted analysis minus the forecast, maybe the square of that, and then you can figure out where you'd want to change variables to improve the forecast based on that. So, yeah, please stop by my room. I'm up in 1401 if you have, further questions. John?
This is probably a dumb question, but since the storm tracks are in a given season or in a given sequence of 5 or 10 seasons, fairly, similar from one year to the next, you can identify geographic locations where such storms as this are most likely to occur, right? Storms that get below 970 or something like that. Can one use an analysis technique like this, or maybe even something simpler, because Terry's question just made me think about this, to identify spots on the globe, given where the storm tracks are, where intense storms are most likely to develop in the cold season, that are most in need of supplemental observations?
I think you could do it. It would do a big climatology of
Yeah.
the forecast bust, and then you could say, these are the observations. And you could even link it, if you had it, you could link this into the idea of a data assimilation system. That, yeah, this is specifically the observations you want, are the ones that would give you an improvement for storms of this type.
Yeah, okay.
Yeah. I meant to say something else about this. Also, just anticipating the talk that Patrick Beatty is going to be giving later this week, is using some of these similar QG diagnostics, not the adjoint part of it, but hopefully there's a nice synergy between these two talks and
I think
knowledge.
there's some nice things to say about that.
Yeah, so for the QGPV work that was done in the inversion back during the early parts of the pandemic, this code is around, we're kind of redeveloping it here consistently, and Patrick and Noah were also instrumental in helping to clean it up and test it out and develop it. One would acknowledge that. So. Any other questions? Well, thank you for your attention. Again, if you have any other questions about this, I'll be delighted to chat with you more.